All right, so today we're pretty much doing the same thing, and the worksheet will actually be very similar to the solubility chart that's over there by Jacob. I'll explain what that is here in a moment after this very long lecture. Practice problems right there, so that tells you something. Here's a really important thing, and we've talked a little bit about acids and bases back when we were doing naming. Anytime that you have an acid and a base, and we'll work with acids and bases a little bit later on, but if you have something, here, let me write this out. So we have sodium hydroxide NaOH, and it's reacting with hydrochloric acid. If it starts with a hydrogen, you're looking at an acid. If it ends with a hydrogen, you're looking at a base. And more importantly, if we have hydrogen and hydroxide, if we put those two things together, what are you going to form? H2O. Or, so if we put hydroxide and hydrogen together, then it's going to make water. And if you want to write it as H2O, that's fine. The HOH is actually the more technical, the more correct way to write water. H2O is more historical. The reason why this is better is because it has your hydrogen, and this one has your hydroxide in it. So I'm okay either way. But do realize this. If I take, say, sodium hydroxide and hydrochloric acid, and if I have high concentrations of these two items or things, and I pour, say, the sodium hydroxide on one arm, it could do some serious damage. If I pour the hydrochloric acid on the other arm, it could do some serious damage. But if I mix these two things together, it would be safe to drink. Okay? So this is a reaction that's very important to our own bodies because, again, when we eat acidic foods or even basic foods, we have things in our body, buffers, that will actually react with this and neutralize whatever acidic thing that we're eating. Those of you who don't have the ability to neutralize acids, what do you have to take? Antacids, yeah. So you need something to help neutralize those acids. A lot of us already have that in play. But keep in mind, this could do nasty things to you, this could do nasty things to you, but if you put them together, then it's making something that we need. Okay? Yeah, it's actually salt water or ocean water, if I were to use this. So the other thing would be the sodium and the chlorine. So I'm actually just making saline solution. It'd be salty, but it would be safe to drink. Don't drink anything in chemistry labs. Except mercury. Very good. All right. So that's it. Let's look at the practice problem. Okay. I think fish do it. Yeah. All right. So the only practice problem today is this, where it says write an ionic equation and a net ionic equation for the reaction of lithium hydroxide and hydrochloric acid. So again, I would recommend writing this out first before we do anything. So lithium hydroxide. What's the charge on lithium? +1. Hydroxide? -1. Good. And then we're going to react with hydrochloric acid. Now, even though I wrote it out, I still want you to make sure you know the charges. So hydrogen is +1. Chlorine is -1. So these are really nice reactions. And we do have a double replacement reaction because we have a metal with a nonmetal, another metal with a nonmetal. So what will the products be? So it could be HOH. We're going to put these two guys together. Okay? And then the other will be LiCl. Okay? So lithium chloride. Okay. Now, just to be careful, I would still go back and check the solubility table just to make sure that we know that water is soluble. It's water. All right? It's not going to form a solid in liquid water. It's not going to form precipitate. However, be sure that you're looking at your table, and remember that all three of these apply to the same information. So, but we're only looking at the chlorine. So is chlorine is lithium, silver, lead, mercury, or copper? No. So it has to be any other positive ion, which means that the lithium chloride is soluble, which means it does not form a precipitate or does not form a solid. So in that case, will we have some spectator ions in this solution? So we'll go back, and now we'll write it out. So here, since I do have liquid water form, I want you to circle it, but not write PPT, but I want you to write an L. What do you think the L represents? A liquid. Yeah, it actually forms a pure liquid. So anytime you see these, where it's a solid, a liquid, those are pure substances. All right, so we're making pure water, or not necessarily distilled water because we do have those spectators in there, but we're making pure water. So when we write these out, okay, so now the ionic equation, lithium ions plus hydroxide ions plus hydrogen ions, again, looking at these. So there are my reactants, same thing that we did yesterday. And anytime that we form a precipitate, or in this case, pure water, keep it together. And then the lithium and the chlorine, how will that look? Very good. So we'll have it. And so our spectators, again, are the lithium, the chlorine, because they look the same on both sides. They don't change. Lithium ion, chlorine ion, chlorine ion. So the net ionic equation, scoot that up a little. Yeah. And if you don't like writing this OH plus H, because some of you are like, oh, I don't like writing that first, then okay, if you need to, you can switch it and do this. That's still the same thing. Okay. Because the plus sign just means what? And. Yeah, it just means hydrogen and hydroxide, or hydroxide and hydrogen. So as long as it's on the correct side of the arrow, I don't care what order you put it in, but when we write out the compound, make sure you write it out correctly. Don't do this. Like if you had your OH and your H, don't write OHH. Don't know what that is. Don't do that. We always write the metal first. Okay. Questions on that? So it's very similar to what we did yesterday, just now we have water in play here. All right, let's take a look at the worksheet, because I want to talk about what the heck that thing is. Okay. So here we have the solubility worksheet. And let me blow that up a little bit. And I'll work a couple of these out for you. Okay. So here's what this is. It's called the solubility worksheet. And let me kind of scoot this up. Along the x-axis, you'll notice you see temperature here. And I apologize, the last 0 in the 100 got kind of cut off there. So we have temperature. And along the y-axis, we have grams of the solute. And again, solute is the thing being dissolved. And what these are all being dissolved in is 100 grams of water. Okay? And as the temperature rises, typically, what is happening to these curves? Are they going up or are they going down? For the most part, they're increasing. And this is going back to what I talked about yesterday, that if you took like water and then added sugar to it, there would be a certain limit to how much could dissolve. But if I heated up the water, I could dissolve a lot more sugar in it because, again, as you increase the temperature, you increase how much you can dissolve in that solution, or in this case, water. Now, you'll notice that there's some dashed lines on here that actually drop or decrease. What do you think these are? Give you a hint. Yeah, it's up in the table there. It's gases. So gases are the opposite of solids, where if you increase the temperature, gases get excited and they speed up and they leave the solution. So they want a much cooler solution to stay dissolved in it. Okay? That's why we drink our carbonated beverages cold. If you drink them hot, all the carbonation is going to go out of it. All right, so here's what we're looking at. So let's look at, I'm going to skip number 1 because that's easy. You'll like that one. Number 2 says, how many grams of potassium chloride can be dissolved in 200 grams of water at 80 degrees? All right, so here's our strategy. So the first thing is we have to find out where the heck potassium chloride is. So where's potassium chloride at on this maze of things? Yeah, it's right here. So if I draw a line, that's a terrible line. But it's in that area, and I'll erase that here. I just want to make sure that you draw your eye to that. So potassium chloride is right here. Let me zap that because I can't draw a straight line on that. And the question says, how many grams of potassium chloride can be dissolved in 200 grams of water at 80 degrees? So let's find 80 degrees, which is right there. And this is for 100 grams of water. Okay, so let's find out, first of all, how many grams of potassium chloride can be dissolved at a temperature of 80 degrees in 100 grams of water. So if I come over here and I find my potassium chloride at 80 degrees, it's approximately in that spot right there. Just above 50. What would you guesstimate that to be? 52, 51, somewhere in that ballpark. And this is for every 100 grams of water. So if I said I had 52 grams of potassium chloride dissolved in 100 grams of water, if I doubled this amount of water, I just simply multiply by 2. So in this case, if I had twice the amount of water, I could actually dissolve 104 grams, approximately. Okay, now I don't want you getting too technical and go, well, Mr. Craig, that looks like 52.3758 grams. You're just blind, sir. Yeah, I probably am. But again, I'm looking for this concept right there. All right, so that kind of helps you with number 3. I'm not going to do number 3 for you. Okay, so let's look at another one. Not going to talk about number 4. How about number 5? It says at 30 degrees, 90 grams of sodium nitrate is dissolved in 100 grams of water. So let's do this first. Let's find 90 degrees. Okay. And it says 90 grams of sodium nitrate. So where the heck is sodium nitrate at? Oh, I'm sorry. Yeah, 9. You're right. Went to the wrong one. So 30 degrees. So we want to go to 30 degrees. Let's say we're not going to be able to find it at 90. Okay, so 90 grams of sodium nitrate. So let's go up 90, 90, 90, 90. So right about there. Okay. And in 100 grams of water. So the question is this solution saturated, unsaturated, or supersaturated? So here's how you figure this out. The curve itself represents the upper limit for how much can be saturated at a particular temperature. So in this case, if I'm looking at potassium chlorate, this is the upper limit, or this represents the point where it's saturated. So anything below that would be considered what? Unsaturated. Good. So looking at the end, if it's on the line, it's considered saturated. Above the line, it would be supersaturated. So what is the answer for this one? Unsaturated. Because we can dissolve, looks like maybe 3 or 4 more grams. Probably not 5 more, but definitely there's room. If we add some more crystals, it would dissolve. So in that case, it would be unsaturated. Okay. Let's do one more. Unless you want to do the rest. Do what? Chart at the bottom? No. One more. All right. Let's do number 6. Okay, let me scoot that up a little so it's above my little square here. All right. So it says a saturated solution of potassium chlorate is formed in 100 grams of water. So let's find the potassium chlorate, which is right there. That guy. Again, I can't draw that line, that curve right. So there's your potassium chlorate. And it says if the saturated solution is cooled from 80 degrees to 50 degrees, so it's cooled from 80 to 50, how many grams of precipitate are formed? So again, as we look at this, and again, there's our curve. So at 80 degrees, we have about, how many grams do you think that is? 42? Okay, let's write that down. So we have 42 grams. And as it cools down, we can't hold as much in solution. So it's kind of like making the rock candy. As the solution cools, crystals of sugar start to show up or precipitate. And then at 50 degrees, it drops down to about what? 22. We'll go with 22. So at 50 degrees, we can dissolve 22 grams. And at 80 degrees, we can almost double that. So if we were to heat this up to 80 degrees, and get it saturated, and then cool it down, how many grams of precipitate or solid should you see in the container? 20. Very good. So you just take the difference. that make sense? Okay. All right. So I think that might be enough information to make it dangerous here to answer these questions. So the homework for tonight is the threes and the rest of this worksheet.